Hi, and welcome back. The simplest numerical series with the terms with variable sign is a series with alternating signs. By this we mean a sum of the form b0 minus b1 plus b2 minus b3 and so on, where the b's are positive and the alternating sign is represented by this sequence of signs plus, minus, and so on. We can represent this as in a compact form as the sum for k going from 0 to infinity. We have the alternating sign, which is this factor minus 1 to k times bk, and here we will assume that they have a constant sign, for example, a positive sign. An example of this series is the logarithmic series 1 minus 1/2 plus 1/3 minus 1/4 and so on. That can be easily written as sum for k going from 0 to infinity, the alternating sign minus 1 to k times 1 over k plus 1. Another representation for this is this one. This series is called logarithmic series because it can be proved that the sum is finite, and we will do here, and actually equal to logarithm of 2. This is something that demands a little bit more of tools to be achieved. The most important convergence test for alternating series is the Leibniz test, which is the focus of this video. So let's see what this test says. We have an alternating series, minus 1 to k bk, for bk positive. Now, if it happens that this bk goes to 0 in a decreasing way, so this means that it goes to 0 and it is decreasing as a sequence, then the series minus 1 to k bk converges. For example, in the case of the logarithmic series, we have that bk is 1 over k, and clearly this 1 over k goes to 0 in a decreasing way. So the series is convergent by the Leibniz test. Let's now see a more standard exercise type problem. So we have an alternating series, minus 1 to k plus 1 times k divided k plus 1. Here the bk is k divided k squared plus 1. Clearly this quantity goes to 0 when k goes to plus infinity, but it is not evident if it goes in a decreasing way to 0. Because when we increase k, it increases the numerator, but also the denominator, and it is not clear what happens to the fraction. Now we will illustrate a couple of methods to how to check that this sequence is decreasing. The first one is a direct method, so we see when bk plus 1 is less or equal than bk, and this means that we have an inequality. So this is bk plus 1, it is k plus 1 divided by k plus 1 squared plus 1. This must be less or equal than bk, which is k divided k squared plus 1. Now, we carry this inequality in line, so we have k plus 1 times k squared plus 1, k plus 1 times k squared plus 1, must be less or equal than k times that denominator, k plus 1 squared plus 1, so it is k squared plus 2k plus 1 plus 2. And now you can see here that by doing calculations at left we have k cubed plus k squared plus k plus 1. This must be less or equal than k cubed plus 2k squared plus 2k. So if you now simplify, you see that k cubed disappears, k squared can be simplified here, so we remain with 1 k squared, and the same for k. So at the end, this is equivalent to k squared plus k greater or equal than 1, which is clearly true for every k greater or equal than 1. So the conclusion is that that inequality holds for k greater or equal than 1, and therefore the sequence is decreasing to 0. the series is convergent because of the Leibniz test. There is a second way to verify if this is true. And this way is to think this bk as a function of real variable k and use the tools from differential calculus. So the particular tool we want to use is that a remarkable fact that says that if the derivative of a function is negative on an interval, then that function is decreasing. So we think to this b of k as a function b of variable k, so of type k divided k squared plus 1, with now k is a real variable just greater or equal than 1. We computed the derivative, which is very easy in this case. We have a fraction, denominator is k squared plus 1 to power 2. Then we have a numerator is derivative of numerator 1 times denominator k squared plus 1 minus numerator times derivative of denominator, which is 2k. So at the end we have 1 plus k squared, and numerator is 1 minus k squared. As you can see, this quantity is clearly negative for k greater or equal than 1. So this implies that the function b, as a function of a real variable k, is decreasing. So in particular, this property holds because k plus 1 is larger than k. And therefore, again, we get that the sequence bk goes to 0. It does in a decreasing way, and therefore the Leibniz test applies, and we get the convergence for this series. The Leibniz test has also another important consequence about the numerical evaluation of the sum of a series. Usually, convergence tests do not provide any information about the value of the sum. They may say that it is finite because the series is convergent, but nothing more than this. If you know that the series converges, the value of the sum could be approximated by using partial sums as n. But how can we choose a partial sum as n such that the approximation error is smaller than a given margin? Now, if you consider this difference, this is the difference between the total sum and the partial sum. So what remains is, again, is an infinite sum, which is called also remainder series. So if we want to assess this quantity, we should, again, face the problem of computing an infinite sum. What is nice with the Leibniz test is that it says, under its assumption, the approximation error is, in absolute value, less than the absolute value of the first term of the series not included in the sum as n, that is bn plus 1. Let's see how this information can be used. Suppose we want to determine the sum of the logarithmic series with an error of less than 1 over 100. From Leibniz estimate, the absolute value of the error is less than 1 over n plus 1 in this case. So we just need to choose n in such a way that 1 over n plus 1 be less or equal than 1 over 100. That is, take n greater or equal than 99. Therefore, the partial sum S99 provides an approximate value of the sum with an error smaller than 10 to minus 2. Well, that's it. What can you do now? Well, first, I recommend practicing the use of the Leibniz test with the exercise you see here. And if you want to improve your understanding, you could reflect on the validity of Leibniz test once we remove the condition that bk is decreasing. So what happens if you have an alternating sign series, minus 1 to k bk, with bk just going to 0? And the suggestion is to think about this example. Good luck.